Welcome to this second video in higher order thinking. Today I'm going to be talking on a topic that is never really covered, or it's not even explored very often, and it's the connection between these two objects that are pretty damn amazing. Um, so the topic today is going to be on the connection between determinants and continued fractions. Yeah, right. It's very weird that there'd be a connection, right? Well, apparently there is. And these guys, I consider, are the top two guys that invented the theory of determinants. Arthur Cayley and Joseph Silvestri. There's been mixed things about who created determinants or who first introduced them. Gauss has been thrown out there. Cauchy has, and a few others. But these two guys predominantly made the footprint in determinants. They were big thinkers, as you can see, and they came up with this determinant idea, and there's a special determinant called the continuant that is actually a special form of the determinant, and this special continuant form of the determinant, we call it the continuant, but it's a special form of the term. If you compute this, it has a rather cool connection with a lot of things. So if we explore some of the properties of this thing, you can see that in examples of it in the 2x2 case and the 3x3 case, if you do a few d terms out, you can convince yourself and see that these are the properties of how it looks. It looks pretty straightforward. You keep multiplying those out, but you can eventually you build an actual way of seeing that there's a relationship between higher continuants. And this, if you can see the pattern, is where it goes. The nth continuant is defined recursively by this formula. And if you expand with the first row down the first row, because you can expand the d terms down the first row, you can build this relation, prove this relation. It's not so difficult. And I urge you, or I, as when you get a chance, and if you're interested, you should try to prove that out to see that relation. It's sort of like it is a recurrency equation of like a Fibonacci or Lucas type. So it's really kind of a neat kind of thing, right? To me, it seems like it's pretty damn cool, pretty amazing and stuff. The next thing, we'll do like a little concrete example. And so this one is like just a simple one. And you can see the work of this is, remember when you have a 0x0 matrix, that's not a matrix. And we just define that recursive equation back here as 1. So when you see this out, you can see that we get a 61. Which, if you combine it all, is going to give you 66 for the total answer after you do out all the recurrency equations and stuff. So you should try that out, see if you get the same answers and compare and stuff, and see if you can come up with that recurrency relation between the continuant and like smaller order continuants. Now, the really amazing stuff, the weird connection between continuants and simple continued fractions. And I say simple continued fractions because you are looking at continued fractions where the numerator is always ones. Okay, and these continued fractions are pretty neat and stuff. We're looking at continuants only really work for the finite case, because an infinite continued fraction in this case, you can't really do infinite d terms over infinite d terms and stuff. It doesn't really make sense unless, of course, you're into infinite matrices and that kind of theory and stuff. But to compute them infinitely to get infinite continued fractions in this form doesn't really work out as nicely as the finite case that we're talking about. However, if you did infinite continued fractions in this form, they are into one-to-one correspondence with the quadratic surds, or polynomials of degree 2 solutions. That connection between these types of continued fractions and the relationship between quadratic surds is another topic in continued fractions alone, but I'm not going to go into that in detail. All I wanted to show you is this connection between these continuants, this determinant kind of thing, and the finite continued fractions. So you can actually compute using determinants your continued fraction, or you can go and put your continued fraction in a determinant form, and vice versa and stuff. Let's do a few examples, concrete examples. So we got this continued fraction. It's not a pretty deep order, but when you set it up, we're going to have these 3 by 3 and a 2 by 2, right? Because remember, if we go back, kn over kn minus 1, where x1 to the xn and x2 to xn. Okay, so you got to remember that when we're in that case, we have to, do these things. So you get 30 for the top and 13 for the bottom. So the continued fraction is 30 over 13, and you can verify that by doing the continued fraction out by hand. Now that is k3 over k2 of those numbers. So you should probably sit there and think about it and see how you get the feel for this and how you can set up all your continued fractions in this way and solve them, finite continued fractions, that is. Some neat, cool properties are that it has some symmetrical property, but it's not really a symmetrical polynomial in all of its variables or in every way, but it's symmetrical a little bit and stuff, so that you can prove that out too as well. And that also proves that there's some symmetry in terms of finite continued fractions, how you represent these things. They give you the same answers in these two different forms and stuff. And you should think about that too, the connection between two continued fractions like that. Also, the cool, neat properties, if they're all ones, you get the Fibonacci number, the nth plus 1th Fibonacci number. So you can convince yourself of that by doing the deep term out of the continuance out, the ratio of the continuance out, and you'll see this. Another property is that this holds too, and that's very close to just using the recurrency equation and reducing it and setting it up. So you mathematicians will recognize these properties very quickly and stuff once you've seen this continuant. Now, that's all I really wanted to show you and stuff. I want you to think on it and explore it, because there's many connections to it. But still, there is a determinant book, and it's called The Treason of Determinants. It was written way back in the day, probably in the 60s or so. But it's still the book that is kind of like the Euclidean elements of determinants. And it's just a wonderful book. It has probably any kind of determinant formula and equation that we know and exist. Like, it goes into everything, the hyperdeterminants, every single thing. So if you can get your hands on that, I think they wrote it in Dover now. They have it a Dover edition, and it's just amazing and stuff. I used to see that a long time ago and stuff in libraries. So it was written by this guy, Thomas Murr. I think you pronounce it Murr. And it's just an amazing book and stuff. It covers continuance, it covers hyperdeterminants, it covers everything. So even now today, I would say, most of our known information on determinants is still in that book. Hyper matrices, hyper determinants, continuance, permanence, uh, things that you wouldn't even be aware of. Only some of these things like resultants in the last few years have been coming out, and it's just amazing and stuff that we only go into a small portion of determinants in our classes, and going into different things and stuff. There's a whole level of coolness in this book. So I hope you enjoyed, and I'll see you on the next one.